All right. Okay. I once again repeat that once the session runs out, please just rush back and log in using the same details, or rather the same link. And I request that you notify your colleagues who are not yet into the session to join so that we proceed. Okay, so last week, I think that was Thursday, we looked at this theorem and we basically went through the proof. And in our attempt to go down into the proof, we deduced this, and we said that I'm looking for my, okay, here it is. All right. So when we went through this, we used what we had discussed previously. That was a theorem on what we called sectional continuity. We came up with that. And on getting that, we also further moved on and we deduced what we have in here. This is what we are trying to look for, that if you have a given function, this is a function in form of a unity step. So you have a step and then the actual function. Then we said that the Laplace of that function will be given by this statement here. And this, before we came here, we had already tried to compute some of these step functions directly when we discussed sectional continuity. So on going through this, we came up with our conclusion. And in that conclusion, I told you to edit the notes a little bit. I told you that there was an L missing here. That L is for the Laplace. What we are including here is actually already included. That is just a typo. If you look at what we have up here, the L is actually there. You can see here clearly that the L is there, it is here. So it's just missing down there. So I hope you have some hard copy with you. Okay, so this is what we got. And now we have an example that we discussed. That is not last week, probably maybe last week on Monday. And we want now to reattempt that very example. That is, okay, this is the number. We did this number. If you remember, we computed the Laplace of this one here. And this is where we use the sectional continuity. So we want to now compute this again using our theorem. So we are going to recompute this and we see if we arrive at the same answer, which we actually did last time, and we came up with this answer here. Okay, so we are now going to apply the proof to the theorem that we did on Friday. We actually applied it in a way, we applied it on this one here. If you remember, those who persevered up to the end of the lecture, we already applied this. And when we applied this, this was an exercise, but I attempted this for you. And I demonstrated how this answer comes along. Right. So in today's lecture, we want now to use this one here and we solve. We look at another piecewise function. So this is just in form of a remark. This remark is basically to complement the theorem 1.41. So if we look at the remark, we are saying the step function enables us to represent piecewise continuous functions conveniently. And for example, you have something like this here. So if we have a quick demo of that, say, let's say we have a function. Let's say we have a function. This is a function here. We have a certain function f. So if this is f of t, this is f as a function of t. So we have a t here. Somewhere here we have a t1. Then we have a 0 here. In between here. Can you guys hear me? Are you hearing me, guys? If I could get a yes, that could be good. Guys, can you hear me? Okay, because there is someone who is saying this is who? Is it Giraneza, Cynthia? She, I don't know whether it is a she or a he. He was saying that he can't hear, but I think the problem could be on her side or his side, because the rest can hear me. Okay, I think I can proceed. I don't have to worry much about what's the name? Giraneza, Cynthia. Okay, let's continue. Cynthia, you try to fix whether your microphone or okay, the same I think with Augustine. Okay, I'll have to continue because everything seems fine on my side, and your colleagues can also hear me audibly clear. I'll have to continue. Okay, right. So let's just think of this. If this was something, say, linear, because this continuous function is linear. If we just, for demonstration purposes, let's say we have something like this. So I could have a certain f naught here. If I have a certain f naught, that is f naught, guys. Then maybe I have another f1 here. This is f1. So if I have f naught, the f naught can go all the way up to here, and this comes right there. Then I have a certain f1 which goes all the way up to here, and then in here it comes down there. Okay, so if I have that, then what would it mean? Now look at the function we have here, guys. So if you look at this function here, we are saying f naught. What is f naught? In the interval between 0 to t1, you have f naught. So the interval between 0 to t1, hopefully we are clear, we have f naught here. So we are now populating this. So you have your ft from 0 to t1. It's actually f naught, which is this one here. Okay. So this is the first step. And remember when we discussed step functions. So now from here up to there. But remember we are saying beyond t1, we are saying it will be t greater or equal to t1. So everywhere here, it will be t1. So it means the final destination, according to this, of course, this is t. So if say this is now the t here, then what is the interval here? The interval, oh, oops, this does not have one, but rather I need to clear this a little bit. That one is not there. Okay. So if this is t now, the interval in between here, that would be now the t minus t1. That is the t. This is the t. This is the t minus t1. Okay. So if it is t minus t1, you need to cancel this out. Okay. So if it is t minus t1, that is from here up to here, then with respect to the function here, you actually have f1. Of course, f1 is a function of t. So here it is f1 minus f naught. Of course, these are functions of t, and this is also a function of t. I hope we are together. But now the step function here is u of t1 minus t, which is that one there. So you realize that we actually have now this function here. So it means our ft, it will be the first part of the step function. We know that it is f naught between 0 and t1, which is f naught, that is equal to f naught t. And then here we add the difference here. So the other step is now from here up to this t here. So since it is up to t on this scale, remember this is now like moving from t for t greater than t1. So you are integrating from t1, to infinity. Okay. So that is now this difference, which is that, and then that one there. So if it is, if you have another function, then you do the same. So from this, it is evidently clear, rather now it is obvious from the explanation I've just given, that our ft now will be given by f naught plus u t minus t1 into f1 minus f naught. And if that is the case, then we can go ahead and demonstrate that very fast. Okay, right. How do we go about that now? I'm going to share us this because we now look at this example just using this very one here. Right, so from that, we can clear that, and then we say, how do we go about this? Let's do this very fast. So to get to this, we just substitute. So from here, we basically know that our f naught is that is 2t plus 1. That is 2t plus 1. Then we have now the f1. F1 is 3t. F1, this is 3t. So we need to find f1 minus 3t, that is this minus that. So you have f1 minus f naught. That is the 3t. And this is minus the whole of the 2t plus 1. And what does this give? There is a plus 1, guys, here. What does that give? That gives us t minus 1. Hopefully I'm clear there. So now we substitute. When you substitute this into this one here, what do you get? You end up with this one here. So this one here is exactly that one there. So the f naught, our f naught is the 2t plus 1, which is this. Then we have u of t minus 2. Remember, it is a integral from 2 to infinity. So that is the t minus 2. The interval, if you remember that graph I drew. So you are moving from 2 to infinity, that is the t minus 2. Then you have the f1 minus f naught, that is the t minus 1, which is this one here. Now we go ahead and we solve. So since we have this, we want to compute the Laplace, and we want to find the Laplace of ft. So to find the Laplace of ft, it is very clear here now. We don't need much, but rather simply to incorporate L here. So we want to find the Laplace of that function there, which is L of this function here. Hopefully we are together. Plus again L of the whole of this. I hope I'm very clear there. So since we want to find the L over the whole of this, we go back. You see, if you look at this expression now, my main interest is in the last part, because this is what we discussed now on the Thursday. If you go back, guys, I'm hoping you have a hard copy of your notes. If you look at what we are calling this L here, which is u t minus 2 t minus 1. That is exactly what we discussed in the theorem. That you have L, that is what we have in the theorem here. That you have, that is the theorem part here. You have L u of t, our A is now 2. GT, our GT is the t minus 1. So we have this one here that we are going to relate. So we only did this to recall this and we substitute it there. So u of t minus a is the t minus 1, gt is the t minus 1, and then we have this one here. Hopefully I'm clear there. Okay, let's go back to, okay, we can go back now. So if we go back to what we are trying to compute, that's this part here. So we are looking for L this and L that, which is the Laplace. So we have, we already have L of this here. We have L of that statement there. And we have L plus L, that is Laplace over the whole of this here. Okay, so since this is the case, how do we go about this? We already know what we are supposed to do here in terms of we already know what to do in terms of our function. So you realize that we had by definition that if you have L, this is u of t minus a. T minus a, and this is into gt. This is gt. We said this one simply gives you e to the minus s. This is sa. And the whole thing is L into, this is G. My mouse is a little bit rough today. Okay, this is G into T plus A. I hope we are together there. Okay, so from this, we can tell that our GT is the t minus 1. Is that okay? And the a, since this is minus 2, the a is 2. Okay, guys, this session is going to run out in the next few seconds. Please log back in and we start immediately. The session is ending in the very next few seconds. So as soon as it logs out, please log back in and let's not take much time logging back